Hello and welcome to the video on section 3.9, which is on differentials. The objectives for this particular video are: number one, understand the concept of a tangent line approximation. Number two, compare the values of the differential dy with the actual change in y, which we know as delta y. And we're going to estimate a propagated error using a differential. And the last thing we need to do is be able to find the differential of a function using differentiation formulas. Let's start out by looking at tangent line approximations. Our main idea is that we're going to be able to approximate a function's value for some x value by going through, and for x values that are close to a particular one at x equals c, by evaluating the equation of the tangent line at x equals c. So what we're going to do here, we have it in this case, we have the graph in green. I have my function f of x, and in red I see the tangent line. And so what happens is if I move a little bit off of c, I can go up and I can go and approximate. I can plug that value, that x value, into my tangent line, and my function value and the actual function value of f of x are going to be close together. And so as long as we stay close to c, our tangent line will give us a reasonable approximation of f of x. If we move far away from c, obviously if I move out to this point here, now my tangent line approximation would be here, the actual value would be here. There's a big difference. So as long as we stay very close to c, we know that our tangent line will be in a reasonable approximation. So our tangent line is, we're going to have our f of x is going to be a differentiable function on an interval containing x equals c. Then we know our tangent line at x equals c is going to be y equals f of c plus f prime of c times x minus c. Now if you look at that, you should notice that that is just our standard point slope form of a line. F prime of c is the slope, and then c, x minus c, and then the y coordinate would be f of c. So this is really just the point slope form of a line that we're familiar with, but we're using our function notation instead of x1, y1, and m. Let's take a look at how this works. We're going to let f of x be sine of x, and we want to find the tangent line to sine of x at x equals pi. So in this case, if I put pi into the sine function, I do get 0. I know the derivative of sine is equal to cosine, so f prime of x is cosine of x. And then if I evaluate f prime of pi, I'm going to get the cosine of pi, which we know is -1. So our tangent line approximation here, our tangent line is going to be y equals f of pi plus f prime of pi times x minus pi. Or in this case, I'm going to get 0 minus 1 times x minus pi. Or our tangent line is going to be y equals the opposite of x plus pi. Or if I go through and just use a decimal approximation for pi, I'm going to get y equals the opposite of x plus 3.14159. And we'll use that to help us out. So what we want to do is we want to use this tangent line approximation to approximate f of 4. Well, in this case, our actual value is going to be the sine of 4, and I can take that and put it in the calculator, but doing that, I couldn't do that by hand. It wouldn't be something I could do quickly. But if I use the tangent line to approximate it, I'm going to realizing that our tangent line was the opposite of x plus pi, I'm going to get the opposite of 4 plus 3.14159, which comes out to be equal to negative 0.85841. So I would say that the sine of 4 is about equal to negative 0.85841. Now let's take a look at differentials. Differentials is going to be something that we're going to be using a little bit to help us approximate functions, but also it helps us set up problems that we're going to be doing in the future. And what we have right here is I have a graph in black, which is our function f of x, and in blue we have the tangent line at x equals c. Now, again, as we talked about here, I can approximate, I can use my tangent line to approximate a function's value. So what I have here is I have c, and then I have c plus delta x. So there's our change in x. Now that change in x is going to be one, we can think of it as delta x. It's also equal to the differential dx. And what happens on this, when I look at this, there is a y value called f of c here, and that's this point. Now, if I go and actually plug in c plus delta x, I have an actual change in, that should be change in y, not change in x. So let's fix that. It's going to be delta y. And then what we have here, when I look at this tangent line, my tangent line approximation would give me this point right there. And the change that we use here is dy. Now I want you to notice we're going to use dy is what we use for our differential of y. But I want you to notice on here that in this case, the dy happens to be the rise that we have in the tangent line. So when we know that the slope, we know that the slope of the tangent line is going to be dy dx, evaluated at c. And so that's why this is the run, which is dx, and that would then be the rise, which is dy. That's how we end up getting that, the dx and the dy there. So now we're going to be able to go and define what differentials are. We're going to let y equal f of x represent a function that is differentiable on the open interval containing x. The differential of x, which is denoted by dx, is any non-zero real number. So as long as we're not using 0, dx can be any other number. And then the differential of y, which is denoted by dy, is that dy is equal to f prime of x dx. So one of the things you're going to be asked to do is find the differential of y and x. Well, the differential of x is just dx, so I don't have to worry about that. But the differential of y, to find dy, I want to go through, I know dy is equal to, and as you see right down here, f prime of x dx. So in this case, I have a function f of x, which is x cosine of x. So I want to find the differential of y, which is dy. So that's going to, first thing I'm going to do is take the derivative of x cosine x. So f prime of x by the product rule is going to be 1 times cosine of x plus x times negative sine x. And when I simplify that, I get cosine x minus x sine x. So if I want my differential, dy is just going to be what I got for the derivative, which is cosine x minus x sine x. Take that quantity, multiply it by dx. It literally is basically that you're going to be given a function. If they want you to find dy, you've got to take the derivative of that function and then just put a dx after it. That will be dy. Let's have you do a couple. Right now, what I want you to do is I want you to find the differential dy. So the first function that you deal with, I want you to deal with is f of x is x minus 2 to the 2/3. And the second one is that f of x is secant of x squared minus 1. So pause the video, and I'd like you to go and find dy for each of these two functions. Let's take a look right now at the very first one. In this case, f of x is x minus 2 to the 2/3 power. So the first thing I do is I take the derivative of f, and I get f prime of x by the power rule is going to be 2/3 times x minus 2 to the negative 1/3, and multiplying that by the derivative of the inside function, which is 1, doesn't change anything. And so I know my differential dy is equal to the derivative of f of x, which was 2/3 times x minus 2 to the negative 1/3 times dx. For the second problem, we know that f of x is secant of x squared minus 1. So when you did this one, you should have come up with f prime of x. Let's get that there. F prime of x is derivative of secant. We got to go through with that. It's going to be the secant of x squared minus 1 times the tangent of x squared minus 1 times the derivative of the inside function, which is going to be times 2x. So in this case, our differential dy is going to equal 2x times the secant of x squared minus 1 times the tangent of x squared minus 1 times dx. So that's what you should have come up with for the differential for number 2. The next one is error propagation. Now what's happening here is that when we talk about error that's happening, we do have, whenever we're evaluating a function, we are evaluating an x, and we're going to treat that x as our measured value. That's, we went through and measured it, and we came up with this value. There is going to be some error in measurement. Whenever we take a measurement, our measurement that we come up with, when I measure a length, that length is going to be an approximate value. There is some error in my measurement. And so the delta x is going to represent the error that we're working with. And so the true value, the exact value that we should come, if we had the exact measurement, would be our measured value plus whatever that error is. So in this case, x plus delta x is going to represent our exact value that we're actually working with. So what I have here is that when I take f of x plus delta x minus f of x, we know that's equal to delta y. Now, again, what's inside here, that's the exact value. That delta x is the error in our measurement, and x in both cases here represents our measured value. So what we have here is that when we talk about the propagated error, that is actually delta y. It's the actual change in the y values. Let's see how this works in a problem. What we want to do is we want to find delta y, that propagated error. Well, we're going to let f of x equal x squared. Our measurement that we came up with is 2, and the error is actually 0.1. So our measured value is 2. Our exact value is going to be 2 plus my error, which is going to be 2.1. So in this case, what I have to do to find delta y, I have to go and find f of 2 plus 0.1, which will be just 2 plus 0.1 squared, or 2.1 squared, which will come out to be 4.41. So that is the exact value that we were actually looking for. With my measured value, I got f of 2, which is 4. So delta y is going to be the difference between those two. So it's going to be 4.41 minus 4, or in this case, delta y is 0.41. Should be 0.41, not 0.441. So let's make sure that's changed. In this case, that should be 0.41. Sorry about that. Another thing we're going to be asked to do is to compare delta y and dy for the same problem. So in other words, what we want to do is we want to look and see how close these are. Now, in reality, if you look back at at our diagram from before, you'll notice that as delta x or dx gets smaller, gets closer to 0, delta y and dy are also getting closer and closer to each other. So when we have a very small value for delta x and dx, we know that our values for delta y and dy should be pretty close. So what I have here is f of x is x squared minus 5, x is negative 3, and what I want to do is I want to find delta y, that propagated error, and I want to find my differential for this. So for our propagated error, it's going to be f of x plus delta x minus f of x. And so in this case, our measured value is negative 3. Our delta x is 0.1. So f of negative 3 is going to be negative 3 squared minus 5, which comes out to be 9 minus 5, which equals 4. So I have that second part I know is 4. F of x plus delta x is going to be f of negative 3 plus 0.01, which equals f of negative 2.99. Plugging that into our function f of x gives me negative 2.99 squared minus 5. When I go and square that, I get 8.9401 minus 5, which comes out to be 3.9401. So in this case, delta y is going to be 3.9401 minus 4, which when I do that calculation, I come up with negative 0.0599. Now let's take a look at dy. dy is going to be f prime of x dx. Well, in this case, f of x was x squared minus 5, so f prime of x is just 2x. So the next thing I have to do is find f prime of negative 3, and when I do that, I get negative 6. So I know that dy, the differential of y, dy, is f prime of x times dx, which will be f prime of negative 3 times 0.01, which we already know f prime of negative 3 is negative 6 times 0.01. I get negative 0.06. So what our delta y and dy are very, very close to each other. This fact should not be surprising because of the fact that our dx or delta x was so small. It was pretty close to 0.01. The other thing this does, though, is this leads us to another piece of information that while delta y is equal to this, we can say that delta y is about equal, or that f of x plus delta x minus f of x is approximately equal also to dy. And so with that leads on, next slide, that delta y, since it's equal to that, it's approximately dy. So I can say that by adding f of x to both over here to the other side, I can say that f of x plus delta x is about equal to f of x plus dy. And realizing that dy is equal to f prime of x dx, I know that f of x plus delta x, our exact value, is going to be pretty close to f of x plus f prime of x dx. Let's look at how this helps us out here. In this case, what we want to do is we want to go and approximate the cube root of 8.5. Okay, that one right here, we can go through on this one. If we didn't have a calculator, it'd be kind of hard to get any type of accuracy with this. Well, what we can do with this is with our idea up here is that I know that f of x plus delta x is going to be about equal to f of x plus f prime of x dx. So what I'm going to do in this one is I'm going to let my measured value be 8, because I'm going to choose that one because it's a perfect cube that's very close to 8.5. I know I'm going to let then dx, or delta x at the same time, be equal to 0.5. And then I know f of x, I'm going to let that be the cube root of x, which would be x to the 1/3. And so f prime of x is going to be 1/3 times x to the negative 2/3, just using the power rule. So what I have is that by up here, I know that the cube root of 8.5 is going to be about equal to the cube root of 8 plus 1/3 times 8 to the negative 2/3 power times 0.5. Well, 8 to the negative 2/3 is going to come out to be 1/4. So I have that the cube root of 8.5 is about equal to 2 plus 1/3 times 1/4 times 1/2, or 0.5. Which when I multiply these fractions together, I get 2 plus 1 over 24. And 1 over 24 is about equal to 0.041667. So our approximate value for the cube root of 8.5 comes out to be 2.041667. If you actually go through on your calculator and you take the cube root of 8.5, you're going to find that this actually is a fairly close approximation. It is accurate to 2 decimal places. And so we're not too far off from having a very, very decent approximation of that cube root. This now concludes the video for differentials. In class, we'll take a look at a couple other examples in terms of calculating the differential, doing some of these approximations, and then after that, you'll have time to work on this stuff in the room. So, anyway, I hope you have a good evening, and we'll see you in our next class.